two variable 3 noded linear triangular element, 2D 2 variable linear triangular element with 3 nodes and 2 degrees of freedom at each node. The nodes are placed at the corners of the triangle. The two variables degrees of freedom are displacement in x direction u and displacement in y direction of v. Since each node has 2 degrees of freedom, a single element has 6 degrees of freedom. The nodal displacement vector is given by, so v is equal to u1 v1 u2 v2 u3 v3. We select the linear displacement function for each degrees of freedom as u is equal to x comma y is equal to c1 plus c2x plus c3y. So v of x comma y c4 c3x plus c6y. So u x comma y and v x comma y describe displacements at any interior point x comma y of the element. The above two algebraic equations can also written as, so u of v 1 xy 0 0 0 0 0 1 xy matrix, then c1 c2 c3 c4 c5 c6 the vector. Using steps we have developed for 2D single variable linear triangular element, we can write c1 c2 c3, that is the 1 by 2a r1 r2 r3 s1 s2 s3 x1 x2 x3, then u1 u2 u3 four displacement vectors. Then c4 c5 c6 is equal to 1 by 2a r1 r2 r3 s1 s2 s3 x1 x2 x3. So v1 v2 v3. Using the interpolation functions we had developed for 2D single variable linear triangular element, we can write u of x comma y is equal to n1 u1 plus n2 u2 plus n3 u3. So v of x comma y n1 v1 plus n2 v2 plus n3 v3. So n1 is equal to 1 by 2a or plus s1x plus xy. Writing the above equation in matrix form, u of x comma y v of x comma y. So n1 0 n2 0 n3 0 0 n1 0 n2 0 n3, then u1 v1 u2 v2 u3 v3 in terms of vectors. Then u vector is equal to shape functions matrix and displacement vectors. So v is equal to vx vy then xy. So dou u by dou x, dou v by dou y, dou u by dou y plus dou v by dou x. So dou n1 by dou x is equal to s1, dou n1 by dou y is equal to x1, from which we can calculate the dou u by dou x, dou v by dou y, then dou u by dou y plus dou v by dou x, from which we can calculate the value of v. So that's equal to v then b into a. Then stiffness matrix. So stiffness matrix K is equal to, so integral of volume base B transpose then D matrix then B matrix into dV. So D matrix is the material constitute matrix either for the plane stress case or for the plane strain case depending on the problem in hand. And substituting them back in U, we get u is equal to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. So n1 is equal to 1 minus x bar by a, 1 minus y bar by b. So n2 is equal to y by a, 1 minus y by b. Then n3 is equal to x bar by a, y bar by b. So n4 is equal to 1 minus x bar by a, y bar by b. Stress strain relations. So v is equal to T by E minus epsilon T by E minus epsilon T by E. So this is the standard format insisted here. Then Vx is equal to Tx by E minus epsilon Ty by E minus epsilon Tz by E. So Vy is equal to epsilon Tx by x E plus Ty by E minus epsilon Tz by E. So Vz is equal to epsilon Tx by E minus epsilon Ty by E plus Tz by E. So next one is the plane stress condition. Tx, Ty and Txy are present. Tz is equal to Txy xz is equal to Tyz is equal to 0. So Tz is equal to 0 from equations. So Vx equal to Tx by E minus epsilon Ty by E. So Vy is equal to epsilon Tx by E plus Ty by E. Solving the above two equations for Tx, Ty, we get Tx is equal to E by 1 minus epsilon square Vx plus epsilon Vy. So Ty is equal to E divided by 1 minus epsilon square E Vx epsilon Vx plus Vy. So Txy is equal to Gxy, Gx into Gxy. So we can return as x is divided by 2 into 1 plus epsilon x of xy. So T of xy is equal to E into 1 minus epsilon square to 2 into xy. So from which, so Tx, Ty, Txy is equal to E by 1 minus epsilon square 1 epsilon 0 epsilon 1 0 0 0 1 minus epsilon by 2. It is a matrix form. So Vx, Vy, x of xy.